Welcome to this scientific lecture on Marangoni flows. Today we're going to explore one of the most fascinating phenomena in fluid dynamics, how tiny gradients in surface tension can drive powerful flows in liquids. Before we dive into Marangoni flows, let's make sure we understand surface tension. Surface tension is a property of liquid interfaces that arises from the cohesive forces between liquid molecules. Molecules at the surface experience a net inward force because they have neighbors on the sides and below but not above. This creates a kind of elastic skin on the liquid surface. Surface tension gamma is defined as force per unit length, measured in newtons per meter. For water at room temperature, gamma is about 72 millinewtons per meter. Now here's where it gets interesting. What happens if surface tension is not uniform across an interface? A Marangoni flow occurs when there is a gradient in surface tension along a liquid interface. The liquid flows from regions of low surface tension toward regions of high surface tension. Think of it like this. The high surface tension region is pulling harder on the interface, so fluid flows toward it. This is the essence of the Marangoni effect. Great question. Surface tension gradients can be caused by several factors. Let's examine the two most important ones. First, temperature. Surface tension typically decreases with increasing temperature, so a hot spot on a liquid surface will have lower surface tension than a cooler region. Mathematically, d gamma dt is negative. For water, this derivative is about negative 0.1, 5 millinewtons per meter per Kelvin. Second, chemical composition. Surfactants are molecules that lower surface tension. A gradient in surfactant concentration creates a gradient in surface tension. Surfactants accumulate at interfaces and weaken the cohesive forces between water molecules, thereby lowering surface tension. More surfactant means lower gamma. Let's explore our first fascinating example of Marangoni flows, the tears of wine, also known as Gibbs-Marangoni tears or wine legs. When you swirl wine in a glass, you'll notice that a thin film climbs up the inside wall of the glass. Then, droplets form and run back down like tears. Here's a wine glass with the characteristic tears forming on the inside wall. But what drives this upward flow against gravity? The mechanism involves three coupled processes. Let me walk you through them step by step. Step 1. Wine is a mixture of water and ethanol. Ethanol is more volatile than water, so it evaporates faster from the thin film on the glass wall. Step 2. As ethanol evaporates, the film becomes enriched in water. Since water has higher surface tension than ethanol, the surface tension of the film increases. Water has a surface tension of 72 millinewtons per meter, while ethanol has only 22 millinewtons per meter. Step 3. The higher surface tension at the top of the film pulls liquid upward from the bulk wine below. This is the Marangoni flow. The film thickens until gravity can no longer be balanced, and then droplets form and run back down as tears. Our second example is even more remarkable. Droplets that move on their own, powered entirely by Marangoni flows. Imagine a droplet sitting on a surface. If one side of the droplet has a different surfactant concentration than the other side, you get an asymmetric surface tension distribution. Surface flow moves from the surfactant-rich, low surface tension side toward the high surface tension side. This creates internal circulation that propels the entire droplet forward. These self-propelled droplets can reach velocities of several millimeters per second, which is quite fast at the microscale. This phenomenon has potential applications in targeted drug delivery, microrobotics, and chemical sensing, where you want autonomous motion without external pumps or motors. Our third example is Bénard-Marangoni convection, a beautiful pattern-forming instability that occurs when you heat a liquid layer from below. When a thin layer of liquid is heated from below, the bottom becomes hot and the top surface is cooler. This creates a vertical temperature gradient. Above a critical temperature difference, the liquid spontaneously organizes into hexagonal convection cells. Hot fluid rises in the center, spreads along the surface, and descends at the cell boundaries. Two mechanisms drive this convection. First, buoyancy. Hot fluid is less dense and rises. Second, Marangoni effect. The cooler surface regions have higher surface tension and pull fluid toward them. The Marangoni number quantifies the ratio of surface tension forces to viscous and thermal diffusion. Ma equals the magnitude of d gamma dt times delta t times L divided by mu times alpha. For thin liquid layers, typically less than a few millimeters, the Marangoni effect dominates over buoyancy-driven convection. The resulting hexagonal pattern is remarkably regular and is a classic example of self-organization in non-equilibrium systems. Now let's consider Marangoni flows in confined geometries like microchannels, which are crucial for lab-on-a-chip devices. At the microscale, surface-to-volume ratios are enormous, so surface effects like Marangoni flows become much more important than in macroscopic systems. In a microchannel with a width of 100 micrometers or less, even tiny temperature variations or surfactant gradients can drive significant flows. Researchers can use focused laser beams to create localized heating spots in microchannels. This generates temperature gradients that drive Marangoni flows for fluid manipulation. Alternatively, injecting a small amount of surfactant creates a concentration gradient that can pump fluid or mix solutions without mechanical parts. The velocity versus scales as 1 over mu times d gamma dx times h, where mu is viscosity, d gamma dx is the surface tension gradient, and h is the channel height. Let's turn to practical engineering applications. First, coating processes, where Marangoni flows can be either helpful or problematic. When applying a thin coat of paint or lacquer, solvent evaporation creates temperature and concentration gradients. This triggers Marangoni convection that can create surface defects like craters or streaks. These defects are called Bénard cells, or fisheyes in the coating industry. They occur because the Marangoni flow redistributes the coating unevenly. To suppress unwanted Marangoni flows, engineers add flow control agents to the coating formulation. These are surfactants that equilibrate quickly and minimize surface tension gradients. Another strategy is to carefully control the drying conditions, reducing the evaporation rate and maintaining uniform temperature to minimize gradients. Our second application is welding, particularly gas tungsten arc welding and laser welding, where Marangoni flows play a crucial role in weld pool dynamics. In welding, you have a molten metal pool with a very hot center where the arc or laser beam hits and cooler edges. This creates a large temperature gradient. For pure metals, d gamma dt is negative, so surface tension decreases with temperature. This means the hot center has lower surface tension than the cooler edges. The Marangoni flow is outward from the hot center toward the high surface tension edges. This creates a shallow, wide weld pool. For many applications, this shallow weld geometry is undesirable because you want deep penetration to join thick metal plates. Here's a clever solution. Adding small amounts of sulfur or oxygen to the metal can reverse the sign of d gamma dt. With these surface active elements, the flow becomes inward, creating deep, narrow welds. For pure iron, d gamma dt is negative 0.4 millinewtons per meter per Kelvin. But for iron with sulfur, d gamma dt becomes positive 0.3 millinewtons per meter per Kelvin. This reversal dramatically changes weld pool shape. Our third application is microfluidic pumping, where Marangoni flows offer a way to move fluids without mechanical pumps or valves. In microfluidic devices for biological assays or chemical synthesis, you need to pump tiny volumes of liquid. Traditional pumps are too large and complex. Marangoni pumping uses localized heating or chemical gradients to create surface tension gradients that drive flow. No moving parts required. A focused laser spot heats a small region. The resulting temperature gradient launches a Marangoni flow that transports fluid along the channel. Marangoni pumping is simple, fast, and reconfigurable. You can change flow patterns just by moving the heating spot, without redesigning the chip. The main limitation is that you need a liquid-gas interface where surface tension acts. This is not always compatible with sealed microfluidic systems. Let me show you how to estimate the velocity of a Marangoni flow quantitatively. At the liquid-gas interface, the surface tension gradient creates a tangential stress that must be balanced by viscous stress in the liquid. d gamma dx equals mu times du dz, where u is the velocity parallel to the interface, and z is the direction perpendicular to the interface. If we estimate du dz as velocity divided by layer thickness h, we get the velocity scale. U is approximately delta gamma over mu times 1 over L times h, where delta gamma is the total surface tension change over length scale L. Let's plug in numbers. For water, mu is 1 millipascal second. d gamma dt is negative 0.15 millinewtons per meter per Kelvin. H is 1 millimeter, and we impose a temperature difference of 10 Kelvin over L equals 10 millimeters. Delta gamma equals 0.15 times 10, which is 1.5 millinewtons per meter. U is approximately 1.5 times 10 to the minus 3 divided by 10 to the minus 3 times 10 to the minus 3 divided by 10 to the minus 2, which gives 0.15 meters per second. That's 15 centimeters per second, which is remarkably fast. This shows how powerful Marangoni flows can be, even with modest temperature differences. Sometimes engineers need to suppress Marangoni flows rather than exploit them. Let's discuss strategies for minimization. The most direct approach is to eliminate the driving gradients. Maintain uniform temperature and composition across the interface. Add enough surfactant to fully saturate the interface. When the interface is packed with surfactant molecules, additional gradients have minimal effect on surface tension. Increasing the liquid viscosity damps Marangoni flows. The velocity scales as 1 over mu, so doubling viscosity halves the velocity. In some applications, you can form a solid or gel-like surfactant monolayer that mechanically resists flow. This effectively immobilizes the interface. Great question. Yes, Marangoni flows appear in many everyday situations once you know what to look for. When a coffee droplet dries on a surface, evaporation is fastest at the edges. This creates outward Marangoni flows that carry coffee particles to the perimeter, forming a ring-shaped stain. The coffee ring is a direct consequence of Marangoni flow coupled with contact line pinning and capillary flow. The classic soap boat toy demonstrates Marangoni propulsion. A small piece of soap or camphor placed on water creates a concentration gradient of surfactant. The boat moves toward regions of higher surface tension. If you sprinkle pepper on water and then touch the surface with a drop of soap, the pepper particles rapidly scatter outward. The soap lowers surface tension locally, and the Marangoni flow pushes everything away. Let's summarize what we've learned about Marangoni flows and their significance. Marangoni flows are driven by gradients in surface tension, which can result from temperature differences, concentration gradients of surfactants, or compositional variations. We've seen how Marangoni flows manifest in phenomena like tears of wine, self-propelled droplets, and Bénard-Marangoni convection cells. In engineering applications, Marangoni flows can be beneficial, as in microfluidic pumping and weld pool control, or detrimental, as in coating defects. Marangoni effects become increasingly important at small scales, where surface-to-volume ratios are large, making them critical for microfluidics and nanotechnology. A complete understanding of Marangoni flows requires coupling fluid mechanics, heat and mass transfer, and interfacial science. This makes it a rich and challenging field of research. Let me conclude by mentioning some open research questions that scientists are currently investigating. How do Marangoni flows behave in complex fluids like polymer solutions or colloidal suspensions, where the rheology is non-Newtonian? What happens when Marangoni flows are coupled with chemical reactions that produce or consume surfactants? This creates feedback loops that can lead to oscillations or pattern formation. Can we develop sophisticated control strategies to precisely manipulate droplets or particles using spatially and temporally varying Marangoni stresses? In microgravity, buoyancy-driven flows vanish, making Marangoni affects the dominant mechanism for convection. Understanding this is crucial for materials processing in space. Marangoni flows are a beautiful example of how invisible surface stresses can drive macroscopic fluid motion. From wine glasses to microfluidic chips to welding, these flows are everywhere. They remind us that interfaces are not passive boundaries, but active participants in fluid dynamics, capable of driving complex and sometimes counterintuitive phenomena. Mastering the physics of Marangoni flows opens new possibilities for engineering at the micro and nanoscale, where surface effects reign supreme. Thank you for joining this scientific exploration of Marangoni flows. I hope you now appreciate the rich physics hidden in these surface tension gradients.